All right, welcome back to Math 107. We're at Lecture 11A, if I'm not mistaken. I think we did 10 yesterday, A and B, so 11A today. I wanted to point out to you, as you know, we're now using a new edition of the textbook, and I had not observed that this author had gone back and put in some calculus relating factoring in the textbook. It's on page 53 in the review section. And so I just want to point that out to you. This is a very important concept. I'm on the book, in the book on page 53. And here are some expressions that occur in calculus. Factor completely each expression. So you have another whole set of problems to work on. And also, this is section review 6 in the front of your textbook. And if you flip back a few pages, page 49, these type problems come under factor by grouping. And here's your little calculus symbol. And there's a couple of example 14 and 15. So I'm very happy to see this. Somehow didn't realize it when I was going through the book getting ready for this class. So be sure you go back and practice in section R5 for some of your calculus related factoring. And again, there are lots of little examples at the end of the exercises. Okay, on page, what did I say, 53? All right. Okay, today what we're going to do is look at the cumulative review on page 394. We're going to look at the even problems. If you're doing this by video, be sure you have already worked this so you can check yourself. And then the guys and the students that are in here, if there's an odd problem that you have questions about, we're going to get those at the end. Then we're going to jump into chapter 4, section 1, and we're just going to look at compositions of functions. There's only one objective there. Even though the book has 2 objectives, we're only responsible for objective 1 in this course. And then move on into section 4.2, where we're going to talk about one-to-one functions that are one-to-one and inverse functions. What we're trying to do is get ready to transition into exponential and logarithmic functions from our algebraic functions. Okay? I think these are called transcendental functions. I think that's the word. Okay, so here we go. We're going to look at the cumulative review. I'm on page 394, and we're going to look at the even ones. The first one is to solve the inequality x squared greater than x. Off the sheets, here we go. And I'll pull up the first one. You're supposed to solve the inequality. Okay, here's the first paper I'm going to look at. Number 2. Okay, I want to look, this person went from x squared greater than or equal to x and moved the x over to the left side and put a 0 here. Is that extremely important, everyone? Yes. Yes. If you had gone through and divided this inequality by x, how would you know which way to put the inequality sign? If x was a negative number, you'd have to reverse it. X was positive, you would leave it alone. If x was a fraction, you'd have to reverse the inequality sign. So the only way you can solve this, do you care if I write in red on your paper? Because this is real important, is you must have a 0 on one side of the inequality. Excellent. So then the next thing she did was completely factor. She's using the rule, she's looking for what makes it exactly equal to 0, and that is at 0 and 1. She put solid dots at 0 and 1. And then you did a little sign chart to test those to see which made a true statement. And you always test back in the original problem before you play around with it. Always test back in your original problem. So if you pick a number such as 10 and you square 10, clearly that's greater than 10, so that's true. That's true. That inequality is true. If you pick a number between 0 and 1, like a half, if you square a half, you get a fourth, right? 1/2 squared is a fourth. A fourth is not greater than a half. So that is not true. So between 0 and 1 is not going to work. And if you pick a number less than 0, such as negative 25, if you square negative 25, you get positive 25. Positive 25 is greater than or equal to negative 5. That checks. So your solution is, I guess that little minus there meant you used a negative number. Okay. So and she used a solid bracket here, square bracket, because it says or equal to. So it's negative infinity up to 0, union with 1 to infinity. Looks good to me. Questions, anybody?
Could you explain that again?
Yes, which part?
The plus and minus.
This right here? I think she was just telling me she used some positive numbers, and that might be for the x. She might have picked the number x equal to 3. So 3 squared, which is 9, is greater than or equal to 3. And over here, I think she was just saying I picked up a negative number, such as negative 3, a number less than 0.
Is that required?
What, the little plus or minus? I think I would just either do true or false to the inequality, or just put a little check or X. Yeah, no, it's not required. You just need to know when you plug it in, yes, it does work, or no, it doesn't work. Okay? All right, everybody good? Thank you. Number 4, we're looking for the linear function with slope negative 3, passing through a point. Okay, problem number 4. Okay, it has slope negative 3, passes through the point negative 1, 4. So it looks like to me, I'm going to go down to the bottom. You put it in point slope form because that was the easiest thing to do. Y minus the y coordinate equals the slope times x minus the x coordinate. This problem did not say it had to be in any particular form, so you could have actually stopped right here, or y minus 4 equals negative 3 x plus 1. That's a perfectly good place to stop. Going all the way down to slope intercept is a perfectly fine thing to do, so you're in great shape. You put in your point negative 1, 4, negative 1, 4 right up here. I'm going to color that. And then you did a slope negative 3, you drop 3 over 1. Okay, does anybody see anything that's not totally correct about her graph?
It doesn't go through the y-intercept at 5.
Oh, it must be a arithmetic mistake here.
Yeah, that's what I was confused.
Yeah, okay, there's an arithmetic mistake down here. Thank you. You got to distribute that negative 3 all the way through. So this should have been negative 3 right here. So the problem's not exactly correct. Thank you. Thank you for checking that. All right. So you should stop right here while you could.
So what is the correct answer?
So you have y minus 4 equals minus 3x minus 3. So y equals negative 3x. And when you add 4 to both sides, you get plus 1. And there is your y-intercept. Okay, so when you graphed it, that should have told you, and I wasn't alert as I was doing this, that that was not correct. Thanks, Aaron. All right, what else is not totally correct about our graph here? Let me draw over exactly what she has. Whoops. Except she has it straighter. Okay, that's what she has right here. What's wrong with that?
In a continuous line?
Yes, she's got it with it stopping at these particular points. It looks like a restricted domain. You just want to make sure you send your line past some designated points.
So you don't want like directional arrows on each end of it, but you want it to go through the last points.
Okay.
Unless it's a segment.
I was noticing that the author of your textbook's putting arrows everywhere. You do not really put arrows this direction. Mathematically, arrows only go in the direction that a function increases. So, and when you draw a line, you really don't put arrows on the end, but some of the more elementary textbooks seems to put errors everywhere there are. Okay? But you do extend past the end point. Okay? Everybody good? Perfect. Number 6. Oh, that one's going to be easy. Number 6. We're going to graph y equals x cubed. That's just your good old basic function that goes through 0, 0, 1, 1, negative 1, negative 1. Kind of hard to miss that one, isn't it? Questions? Too easy. Number 8, solve the equation. Let's see here. I'm just going to grab one that's easy to find. Number 8. Number 8. All right, number 8, we notice that we have a, is this a polynomial function or a polynomial equation? It's just an equation. We don't see a y value there. Solving it means we're looking for what values for x make this true. Okay, here's number 8. All right, the first thing this person noticed was x was a common factor in all terms. So factor it out in x. And then notice that x squared minus 6x plus 8 factored further to, or did it?
Yeah, factored.
Factored further to x minus 4, x minus 2. I'm going to put a little star right here. Too many people miss x equal to 0. You're really setting each factor equal to 0. X equal to 0, x minus 4 equal to 0, x minus 2 equal to 0, and then this is your solution. Best I can tell, that looks perfect. Anybody agree, not agree? All right, excellent. Okay, number 10, you got to skip. Number 12. Number 12. 12. Okay, number 12 says, find the equation of the line perpendicular, can you see it? To 3x minus 2y equals 7 that contains the point 1, 5. All right, when I look at this problem, I would get pretty excited on a test because what's the problem here? I have no clue how you got from one step to the other. You have to show all steps. Okay, I can't guess how you're getting where you are, or maybe you didn't even do it. I'm not sure. Okay, so that wouldn't get any credit. Let's go to number 12 on another page. 12. Number 12. Okay, what do you know about the slopes of perpendicular lines?
Negative and
Negative reciprocal. So the first thing this person did was find out what the slope of this line is by solving for y. So let me just double check that. Negative 3 over negative 2 should be positive, right?
Yep.
Shouldn't that be a positive 3/2? When you subtract 3x and then you divide by negative 2, negative 3 over negative 2 should be positive 3/2. So it should be plus 3/2 x minus 7/2. Okay, so the slope of this line is positive 3/2. Whoops. What happened here? Oh, negative reciprocal, but the problem was incorrect up to that point. All right, so the slope of the perpendicular line, and I'll do like this, perpendicular line, should be negative 2/3.
Yeah.
Is that true? All right, so then once you know the slope is negative 2/3, got to be careful with those negatives over negatives. All right, then it's going to pass through the point 1, 5, so y minus the y coordinate equals the slope, negative 2/3 times x minus the x coordinate. And it didn't say you had to put it in any particular form, so you could actually stop right there. So this is not going to be correct because positive 2/3 was used there. Okay, and then the other part didn't ask you to graph it, but if you graph it, they will come in at right angles. Questions on that? Be really careful with those negative and positive signs. All right, number 14. Number 14, you're given a function and you got to do a lot of evaluating. I hope this person got everything right so we can use every one of them. Okay, here we go. Let me make sure it's copied down right. Yes. Move the book over so I can see it. First thing you had to do was evaluate the function at 3. So that just meant you put a 3 in for your x's. So you had 9 plus 15 minus 2. And that looks like that probably is 22. Okay? The next one is to evaluate f at negative x. And I see a negative 1 stuck in there. Is that what we're going to do, everybody? Remember, f evaluated at anything is going to be that anything squared plus 5 times the anything minus 2. Right? Whatever goes in there. So are you putting a negative 1 in here? No, you're putting in the entire negative x. So it should be f of minus x is minus x squared plus 5 times minus x minus 2. If you square negative x, that's the same thing as a negative 1 times x. If you square that, what do you get? Positive x squared. X times negative 5 is minus 5x minus 2, and you're all done. Okay? Remember, I think if you'll do a little set of open parentheses and then substitute the values in, you'll be better off.
Okay. Question.
Yes?
If the minus is in front of the f, like minus f.
Okay, that's part C.
Okay.
Okay? Part C. Part C is minus f of x. Let's go back. What is f of x? F of x is x squared plus 5x minus 2. Minus f of x just means you're going to do like negative 1 times f of x. So if I multiply all this through by negative 1, what am I going to get?
Everything is negative x.
Negative x squared minus 5x plus 2. So the minus on the outside says take your old f of x and multiply it through by negative 1. Does that answer your question?
Only the x's.
Well, only the x's part would be back over here, f of minus x. The difference between f of minus x means that the minus x goes wherever an x was in your original function. The minus outside the f of x means take your f of x and multiply through by negative 1.
So,
Go ahead.
On top.
Excuse me?
I can't see the paper.
Oh,
So it's still plus 5x. Oh no, minus 5x.
yeah.
And
You're-
plus 2.
Right, you're taking a minus 1 and multiplying it times both sides of the equation, and you multiply it all the way through. Does that help?
Yes.
Okay. All right, let's try f of 3x, and I think I'll take a blue sheet here because I'm about to make a mess on this paper. Remember that f of anything is anything squared plus 5 times the anything minus 2. So if you need f of 3x, where are you going to put the 3x? In the parentheses. Okay, what happens when you square 3x? What do you get?
9x squared.
9x squared plus 5 times 3 is
15.
15x minus 2. All right, let's see. This person got it correct. However, the parenthesis right here was missing. It's 3x quantity squared. Yes?
The C part that the person's done, I can't figure that out.
You can't figure out their C part? Me either. Because they substituted a minus 1 in for x, and that was totally not correct. Okay? Thanks for clarifying that. I should have put a big old X there. All right, everybody good? Remember, you're learning from your mistakes. You want to make mistakes before the test and learn from them. Okay, let's look at part E. Oh, good. Looks like we're coming along here on part E. Let's see here. This part right here must be f of x plus h. Be careful that you're labeling what you have. Because if f of x is anything squared plus 5 times anything minus 2, then f of x plus h, you replaced it in there. When you multiplied out x plus h, you get x squared plus 2xh plus h squared. And then you got a 5x plus a 5h minus 2. So here's your f of x plus h, everything put out. All right, you got to be careful about all these equal signs because this line is definitely not equal to the next line. Your next line is f of x plus h minus f of x divided by h. Do you see how you got to make correct mathematical statements? All right, so you recopied f of x plus h, and you did a good job using parentheses. It's minus, and now you put in your f of x, and then you saw that x squared minus x squared canceled out, 5x minus 5x canceled out, and negative 2 plus 2 canceled out. So you were left with 2xh plus h squared plus 5h. All right. Are we good from this step to the next step, everybody? From here to here. Is that good?
Yeah.
I hadn't heard the right answer yet. Is this good?
No.
No. What happened here?
They took out the X. But, I mean, they took
H
out the
only out of one term,
Yeah.
right? It's like you had a problem like 2 plus 3 plus 5 over 3, and you just divided that out and claimed that was 7. That's 7 plus 1 maybe. And that's not true. 2 and 3 is 5, 5 plus 5 is 10. 10 thirds is definitely not equal to 8. The only way you can divide out is when everything is multiplied, because A over A is like 1 times B over C. So I'm going to use a big old red on this one. No. You got to come back here and say H times 2x plus H plus 5H over H. Now, because it's multiplied, H over H is equivalent to 1, and so now you're left with 2x plus H plus 5H. Okay? Everybody good? Questions, anybody? All right, be real careful with that. You can't divide out unless everything is multiplied. Yes?
Why is there still 5H? Wouldn't it just be plus 5?
The reason it's there is because I made a mistake. That should not be there. Thank you. When I factored a H out of the 5, that numerator there, right, there was no 5. So the final answer is 2x plus H plus 5. Thank you very much for correcting me. I appreciate it. Everybody good? That was a test to see if anybody was paying attention, and you were the only one. All right. So we're through with that. Let's go to problem number 16. Okay. Problem number 16 is just to graph that function. All right, and we'll look at this one. 16. Y equals minus 3x plus 7. Okay, if this were given to me on a test, what would I get excited about?
It's not continuing.
Okay, it didn't continue past that end point right there. What else would I get excited about?
It's not labeled.
Okay, we don't have any units on the graph because, you know, along the x-axis don't have to be the same as along the y-axis. So we need, my guess is these are units of 1. So we need to somewhere put these on there. So 1, 2, 3, 4, 5, 6, 7. The axes were labeled, but the units weren't. Okay, y-intercept of 7, slope 3, 1, 2, 3 over 1, 1, 2, 3 over 1. So we're good. What would be the x-intercept here? X-intercept.
Two. Wherever.
X-intercept, you let y be 0, right? 0 equals minus 3x plus 7. Negative 3x equals negative 7. X equals 7/3, which is what, 2 1/3, and you'll notice that went exactly there at 2 1/3. Right? Especially if my line's thick enough. Are we happy? Let's go to problem number 18.
Could we go over problem number 17?
Okay, I will come back. Will you hold on to that thought?
Okay.
Okay, let me get through the even ones first. And problem, I got separated. Okay, here we go. Start over. Problem number 18. 18. Okay, problem number 18 asks us to find average rate of change. Average rate of change is just slope of the line between 2 points, right? And which is the slope of the secant line. And our 2 points are, we're going from 1 to x. So we have the point 1, and when x is equal to 1, you figured putting it into your function that's 1 plus 3 plus 1, which is 5. So you got the point 1, 5. And then you have your function x, and the y value is x squared plus 3x plus 1. Okay? So it's asking you for a general formula to find the average rate of change between 1 and any other value. That's what it's asking you for in the beginning. And then it says use this result to find the slope between x equal 1 and x equal 2. All right, so remember, slope, which is average rate of change, is just the difference in the y's over the difference in the x's. So the difference in the y's, x squared plus 3x plus 1, minus 5 over the difference in the x's. Okay? So this is going to be the slope of the secant line between the point 1, 5 and any other point on the curve. Any other point on the curve would have an x, y value, and here's the function that defines that y value. So that gives me x squared plus 3x minus 4 over x minus 1. All right, everybody good so far? Now it says use this to find the slope between the points 1, 5 and 2, f of 2. Well, the advantage of having this formula is we have our value for x now is 2. So we don't really have to go find out what the y value is. We can just substitute 2 in for x. We found the formula between 1 and any other value of x. So we'll just put in a 2 for x at x equal to 2. So we get 4 plus 3 times 2 is 6 minus 4 over 2 minus 1. So it looks like we have 6 over 1 or 6. All right, let me go a step further on that, and then I'll answer your question.
2 come from?
Because the problem said, then use this formula to find the slope of the secant line between 1 f of 1, 2 f of 2.
Oh, okay.
So I just substituted the 2 in for x. Okay, here's the other thing that could have happened. F of x is x squared plus 3x plus 1. And you found that f of 1, you already figured that out, was 5. F of 2, 2 squared is 4 plus 3 times 2 is 6 plus 1, which is 10 plus 1 is 11. So if the problem just said find the slope between the points 1, 5 and 2, 11, remember this is a parabola that opens up, we're looking at the slope of the secant line between those 2 points, you would have just said the slope is 11 minus 5, 2 minus 1, and you got 6. But what the problem was trying to get you to do was just come up with a formula so that you could quickly find the slope of the secant line between the point 1,5 and any other point on the graph. So that was just a general formula from one to any other point, and then they just sort of had you verify that using this other point. Does that make sense, everybody? Everybody good? Which way do you want me to go?
Yeah, copy that.
This page? Okay. All right. Questions for me on that? All right, we're going to look at problem number 22. Problem number 22. Let's pick this one because I quickly see number 22. Have you finished copying? Okay. Problem number 22 is to sketch the graph of minus 3 times the quantity x plus 1 squared plus 5. And this person did such a beautiful job saying they're going to sketch the basic function negative x squared. That's okay. You could have started out with just x squared. Okay. A vertical stretch. Couldn't read it, sorry. Vertical stretch by a factor of, and in this case that would be a factor of, if you're calling that minus as your basic function, then that would just be a factor of positive 3 because you already got your minus in there. So do you remember if you did it with a positive x squared and then did a factor of negative 3?
Positive, yeah.
You did positive. That's what I would have done. I would have started out with y equals x squared, and then I would have done a vertical stretch by a factor of negative 3, just meaning you're going to multiply your y values by negative 3, which is what you did right here. Okay? Then a, horizontal shift to the left of 1. That has to do with y values. So you just, I love the way you did this. You just pull these problems right here, these points, and then horizontal left 1. That means that you're going to be subtracting, what did you do? Oh, you did that down here. Maybe you did the vertical next. I believe you did the vertical next. Okay, vertical shift up of 5. You added 5 to each of those y values right here. Added 5 to each of those y values. And then you did the horizontal shift left by 1, and you subtracted 1 from each of the x values. Perfect job. All right, so she just followed her points along and did what she said. Okay, so basically you would graph y equals x squared. Then the vertical stretch by a factor of negative 3, you multiplied all the y values by negative 3, which then sent it down. And then you did a shift to the left of 1, sent it over 1, and then you went up 5. That probably is correct. Okay, and I especially love the way you followed all your points through, which meant you understood what you were doing. All right, any questions on that? You guys are really good at shifts. Okay, all right, good. How's that? All right, let's go to problem number 24. Number 24, the demand equation. 24. It says that the price P is minus 1/10 x plus 150 as long as x is between 0 and 1500. I'm just going to jot that down. Okay, the price P, x is the quantity sold. Revenue. Excuse me, how does, in words, what's revenue function?
Y equals X.
Price times x. Right, so you just multiply this through by x and you get negative 1/10 x squared plus 150x. Perfect. What is the revenue if 100 units are sold? You just plug and chug 100 in for x, and I'm just going to trust that that came out right. Didn't remultiply that, but probably did.
Yeah, that's right.
Thank you. See what quantity x maximizes revenue. Somebody tell me what's going on right here. Can you see it? There's a negative 150 over 2 times negative 1/10. What's going on here? What is that? I know what it is. I just want you to tell me what it is.
The vertex?
The vertex. This person noticed that our revenue function is a parabola. Negative 150, negative 1/10 x squared plus 150x. It's a parabola that's going to open down. So the question is, what value of x maximizes the revenue? The graph's going to do something like this. You want to find that x value, and that's going to be at the vertex. And remember the formula, x is negative b over 2a. So the b is 150, so there's a negative 150 over twice negative 1/10. And then I'm just going to assume the arithmetic was done correctly, which it probably was. And we're going to assume that that is at 750. Okay? So what is the value of x that maximizes the revenue, and then what is the maximum revenue? So once you know x is 750, you just substitute back in for x, and all the arithmetic was done here, I assume correctly, so it looks like 750, looks like a comma's in the wrong place. Oh, here it is. You gave me the ordered pair. The maximum revenue is $56,250. Be sure you're clear on what is what. You gave me the point, but let's make sure you understand that you're answering the question. 750 units sold will give us a revenue of $56,250. Yes?
Why do you have to do the math to find the 750?
Because the question says, what is the maximum revenue?
I don't know. It just seems kind of obvious to me because this symmetrically in between 1,500 and 0 is 750.
Well, I think you're making a generalization. It may be in the case of this parabola.
Because wouldn't it symmetrically have to go through the vertex?
Well, if you're sure, okay, the question is, if you're sure that this intercept right here is the 1,500, where this is a restricted domain, then, if that is your zeros, yes, you are correct that the vertex is on the axis of symmetry, which would be halfway in between. But we didn't take a second to see if that was x-intercept of 1,500. Okay, if you knew that, then you certainly could do that, and then it would be quicker to do. All right, good point, thanks. All right, everybody good so far?
What does it say on that last, C?
See, I wanted to make sure you were answering the question. It is at 750, that's the number of units you need to sell for maximum revenue. And then the maximum revenue is, you put your 750 in for your X, and it comes out to be 56,250 according to this paper. Okay?
And the number next to that?
Right here. Well, that confused me for a second there. That is the point 750, comma, 56,250. So they gave me the ordered pair for the vertex.
Oh, okay.
And what I was saying is, on a test, how do I know that you know this answers the first part of the question and this second? You need to be very clear about what you're saying. Is that good? Mm-hmm. Thank you. And then number D, letter D says, what is the price to receive the maximum revenue? So you would just go back to the price function. And this person didn't show me all the steps. What do you think they did? Put a 750 in for X, because X is 750. And that does come out to be 75. That's the price that needs to be charged for the maximum revenue. Everybody good? Okay, let's go back to, that takes care of all the even problems. You had a question about number,
Question I had
was it 19?
I have a question about 15 and 17 and
15.
23.
Woo, lots of questions, okay? Okay, question 15.
B and D.
All right. F of x equals x plus 5 over x minus 1. You had a question about B. B says, is the point 2, 6 on the graph of this function? All right, how do you tell if a point is on the function? If this point is on the graph of this function, shouldn't you be able to substitute it in and you get a true statement? So you would have to say, is 6 equal to 2 plus 5 over 2 minus 1? And if it is, you're going to get 7 divided by 1. 7 is not equal to 6, and you go, nope, it is not. Okay? And which other one there?
D.
D. D says, if f of x equals 9, what is x? So try to realize that you're just making substitution. F of x,
Y equals 9.
right, so a 9 goes right here. 9 equals x plus 5 over x minus 1. And now you solve for x. Is that good?
But how, so I was confused on what's the steps to actually solve for x on that? Because I wrote that down. I did get that on my paper. That
Okay.
9 equals x plus 5, x minus 1, but I wasn't sure what to do after that.
Okay, so you have a rational equation. How do you eliminate the fraction here? What's your golden rule?
To find the common denominator?
Okay, and multiply all the way through.
Okay.
So we'll multiply both sides by x minus 1. Do unto one side of the equation as you do unto the other. So you would get 9x minus 9 equals, and then the x minus 1's cancel out over here, x plus 5, and then work your way down.
Okay.
Is that good? All right, anybody else on 15? Anything? Okay, your next question was, I'm glad you're asking these if you didn't know. What's another one? 19?
That was 15, number 17.
17. Number 17. F of x equals 2x squared minus 4x plus 1. Determine whether the graph opens up or down by finding its vertex, axis of symmetry, y-intercepts, and x-intercepts, if any. Graph it. We want to graph it. All right, what's this the graph of, everybody? Parabola. Is it going to open up or down? Up, because the coefficient in front is positive. What is the y-intercept?
1.
You just let x be 0, y is 1. All right, so I would say as soon as you know something on the graph, I would put it there. So let me just draw this. So as soon as you know a point, go ahead and put it there. All right, how do you find the x-intercepts?
Factor.
Try factoring it, because you're going to set y equal to 0. Is this going to factor?
No.
It doesn't?
Yeah, that's factor.
I think it does, doesn't it?
I'm pretty sure it does.
Oh, no, it doesn't. I was thinking that was a 4. All right.
Yeah.
So if it doesn't factor and you needed to know what the x-intercepts were, what would you do?
Quadratic formula.
Quadratic formula. X is equal to negative b, which is 4, plus or minus square root b squared, which is 16, minus 4 times 2, which is 8, over 2 times 2, which is 4. So you get 4 plus or minus the square root of 8 over 4. And if you wanted to approximate that, you just go to your calculator and plug and chug. 4 minus the square root of 8 over 4, and x equals 4 plus the square root of 8 over 4. All right, I didn't bring my calculator, so we're just going to move on so that we can sketch the graph pretty easily without knowing exactly what our x-intercepts are. How do you find the x-coordinate of the vertex? What's the formula?
Negative b over 2a.
negative b over 2a. And negative b is 4, 2 times 2 is 4. So the x-coordinate of the vertex is at 1. You asked this, are you okay? How do you find the y value once you know x is 1? Plug and chug. 2 times 1 squared minus 4 times 1 plus 1. 2 minus 4 plus 1 must be equal to a negative 1. So the vertex is at 1, negative 1. Okay, well we got enough now to quickly sketch the graph. Everybody good so far? 1, negative 1 is right here. Parabola opening up. All right, what's the axis of symmetry? What's the equation for the axis of symmetry?
Negative b over
X
2a.
equal to positive 1, right? Where your vertex is. Now, from the vertex, if I go left 1, the y value is up 2. So what does that tell me if I go right 1? I'm going to go up 2 from there. So we know the point 2, 1 is also on the graph because you came over to the left 1 unit and you went up 2 units. So if you go to the right 1 unit, you also go up 2 units because a parabola is symmetric about its vertex. So the parabola is going to go like this. Okay?
So,
Yes?
Where did you get that you go up 2 from?
Because we already knew the y-intercept. So if I'm at the vertex, because a parabola is symmetric about the line going through the vertex, if I went over 1 and I knew the y value was up here at 1, that's going up 2 units
Okay, so you're saying from the origin.
from my vertex. Right.
Okay, that's what I meant to say. Just
Yeah.
basically from where the parabola starts. Yeah.
Right.
Okay.
Correct. Okay. Anybody questions on that? All right, is there another question on the cumulative review? Cumulative review.
Number 21.
Number 21. Okay, number 21. You have a piecewise defined function, 2x plus 1, if minus 3 is less than x less than 2, negative 3x plus 4, if x is greater than or equal to 2. Okay. Which parts of this did you have a question about? All of them? Or
All of them.
what's the domain, everybody?
X cannot equal or all real numbers.
You just look right here. It's going to tell you exactly what the domain is.
All real numbers greater than negative 3.
Yep, it's all numbers greater than 3. Because this says you're very close to negative 3, but that goes up to 2. But it doesn't include 2, but then the next part is going to pick up at 2 and go on forever. So if you wanted that in interval notation, that's negative 3 to infinity. Okay, that's your domain. Is that good? You read it off right there. B, locate any intercepts. Any intercepts. Well, if you're looking for a y-intercept, that's where x is exactly equal to 0, right, on your y-intercept. So are you going to use 2x plus 1, or are you going to use minus 3x plus 4 to find the y-intercept?
2x plus 1.
Okay, x being 0 has to fall in the interval between negative 3 and 2. So we would use y equals 2x plus 1, or 2 times 0 plus 1, or 1. So the y-intercept is 0, 1. Correct? Okay. How about x-intercepts?
7.
Okay, we don't really know which of those we're going to use, but we do know that we let y equal to 0. So we could have 0 equals 2x plus 1. Solving that, you get x equals negative 1/2. So it may pass, it depends on where this little curve is here. X is at negative 1/2. That is in there, so that's good. And then if we let y equal to 0 for the next part, we get 0 equals minus 3x plus 4, or x is equal to, what, 4/3? 4/3, and that's 1 1/3, but that doesn't fall in the region x greater than or equal to 2. So it looks like the only intercept we're going to have on the x-axis with our restricted domain here is at negative 1/2. Okay, so then it says graph it. Not a problem for us. But I think it was easier to graph before you did everything and then answer the questions. All right, let's see if we can sketch this. All right, I wish I had my pencil here, but I don't. Just lightly sketch it with a pencil first. That works good. Anybody got a pencil real close? You got one? Great, thank you very much. All right, if we graph y equals 2x plus 1, the y-intercept is 1, slope is 2, so we go up 2 over 1, or down 2 over negative 1. I'm just sketching the graph of y equals 2x plus 1. But it said you better only keep the part between negative 3 and 2. Let's see, I may want to go down a little further here. Negative 2, negative 4, negative 5. If x could be equal to negative 3, the y value would be negative 5. So we'll put my little lines off a little bit here. This is the point negative 3, negative 5. If I put a negative 3 in for x, so negative 3, negative 5 is here. And then the slope, it's going to go through the y-intercept. The line's going to go something like this, and we're going to stop when we get to 2. And 2 is actually up here at 5. Okay, probably be better if you had the graph paper and the straight edge. You're only keeping that part of the line between x at negative 3 and x at 2. If you had a point there, it would be 2, 5, but we have an open circle. Is that part okay for 2x plus 1? It's the graph of the line y equals 2x plus 1. Okay, then when you're bigger than or equal to 2, you're going to have negative 3x plus 4. So let's just pick a point. When x is 2, the y value is negative 6 plus 4, which is negative 2. So 2, negative 2. That's definitely on there. When x is 2, the y value is negative 2. And the slope is negative 3 here, so we will go down 3, 1, 2, 3 over 1. So you have the point 3, negative 5. Negative 3 times 3 is negative 9, plus 4 is negative 5. So that line looks like this. Okay? That's a straight line, it just goes off. Okay, so we only had that one x-intercept because it was defined there, and there's your y-intercept. Is that clear? Okay, notice that here I went beyond endpoint because it said x greater than 2. Here I had sort of a restricted domain on that part. Everybody good? All right, we're going to stop right there, and we're going to start in chapter 4 at the beginning of the next section. Too bad. Alrighty, welcome back to Math 107. We're at Lecture 11B, and we are going to, I'm sure, during this hour, cover section, Chapter 4, Section 1, Composition of Functions, and get it, hopefully finish Chapter 4, Section 2. The second test is going to end at Chapter 4, Section 3, I believe. We'll finish that up tomorrow, and then we'll go back and answer specific questions, getting ready for your test. Okay, composition of functions. We'll start here. Chapter 4, Section 1, and composition of functions. And I like to say that we are just in the creating business. We're creating new functions. Creating new functions from given functions. All right, and I also claim that this section, by the way, we're only looking at objective number 1. If you're on page 396, there are 2 objectives listed in the book, but we're not going to worry about the domain of the composition of function. We're only going to worry about forming a composition of function. We're going to be using that when we talk about inverse functions in the next section. And also, once you start taking derivatives in calculus, your general power rule turns out to be, can be explained, for derivatives, can be explained using a composition of functions. All right, normally we go to preparing for this section, but I feel like we just worked a problem like this in tape 11A, but let's just verbally say what we would do on page 401, number 2. Preparing for this section, 401, number 2. When it says find f of 3x if f of x is 4 minus 2x squared, where are you going to put the 3x, everybody? Where do you put the 3x?
Where x is.
Where the x is. So if f of x is equal to 4 minus 2x squared, f of any element is 4 minus 2 times that element squared. And this problem was asking us for when x is 3x, when we're replacing the domain with 3x. So we put a little 3x right here. I meant to do that in a different color. I don't know if it's showing up on the tape different. It's not, is it? Okay, 4. How do you handle this last term? How do you simplify that part?
Square the 3x.
Okay, so it's minus 2 times, and when you square 3x, you get
9x squared.
9x squared. So we get 4 minus 18x squared. Okay, everybody good? Everybody good. Okay. All right, I wanted to jump into composition of functions with an example to indicate you already know how to do this problem without, you know how to do compositions by common sense. You'll turn to page 403. And we're going to look down at example 3. I'm on page 403, example 3. And this has to do with the surface area of a balloon. The surface area S, we're on page 403, number 63. The surface area S of a hot air balloon is given by, the surface area is defined in terms of the radius. The surface area is a function of the radius, is 4 pi r squared, where r is the radius of the balloon. Okay, then they tell us another formula. If the radius r is increasing with time, so air is being pumped into this hot air balloon, the radius is increasing according to this formula that r is 2/3 t cubed when t is greater than or equal to 0 seconds. Now the question says, I'm very interested in the surface area of this balloon after t seconds. See, the surface area is in terms of the radius. The radius is in terms of time air is being pumped in. But we want to come up with a function that will give us the surface area based on the time. Do you see the question? All right, so we're just going to take it apart and use some common sense. Hopefully we have some. All right, number 63. So we're on page 403, number 63. The information we have is that the surface area is a function of the radius. The radius is a function of time that air is being pumped into the balloon. Okay? Now, I'm going to pick it apart, and then we're going to come back and answer the questions. Maybe I want to say, what is the surface area after 1 second of pumping air? I don't believe they said they were pumping air in there, did they? Well, that's what they were doing. Helium, I guess, is what they're putting in there. All right, so how am I going to just use these formulas to come up with what is the surface area after 1 second? Because surface area is in terms of the radius. Radius is in terms of time. What would you do?
Substitute 1 in for t.
All right, so the first thing says, okay, first of all, I can find the radius after 1 second, correct?
Mm-hmm.
The radius is 2/3 times 1 cubed, or 2/3, and this is in terms of, what's R in terms of?
T.
No, radius is in terms of inches, what?
I think it specifies, does it?
Meters.
Does it?
Meters.
That's a big balloon.
Okay, T is in seconds, R is in meters, and surface area would be in square units. Surface area square units. All right, so after 1 second, we know the radius of our balloon is 2/3 meters. But then the question is saying, okay, when the radius is 2/3, what is the surface area? So we would come back and say, okay, the surface area at 2/3, does that make sense? Is equal to 4 pi times 2/3 squared. And that would give me the surface area after 1 second. Because it required me 2 steps to get there. I had to first find the radius after 1 second. Then once I knew the radius, I plugged it in here. All right. Now what this problem is doing in number 63 is it's saying, well, hey, why should you have to go through so many steps? Is there a way that I can redefine surface area in terms of time that air is pumped or helium's pumped as opposed to radius? So problem on page 63 is asking me to come up with the surface area in terms of T instead of R. So what we're going to do, we want just a general function, is we're going to do what is called a composition of functions. And if you look, isn't this 2/3 right here? That really came from the formula for radius. The 2/3 really came from the formula from the radius. Isn't that true? So all we're going to do is we're going to find the surface area evaluated at the radius, or the surface area evaluated at RT is 2/3 T cubed. Right? RT, let me write those back up here. S of R is 4 pi R squared. R of T is 2/3 T cubed. So now I want to evaluate the surface area based on time. So to find out the time, I've got to find out the radius, I have to plug the time in. And now if I want S evaluated at 2/3 T, S evaluated at anything is going to be 4 pi, and in the place of the R here, I will put 2/3 t cubed. I'm plugging in what RT really is. That's the
What?
function that gave me the radius.
Mrs. McCollum, wouldn't that be squared?
Did I copy it wrong?
Yeah, it's
Squared.
Yeah.
Yeah.
Squared.
Thank you. So S evaluated at anything is 4 pi times the anything squared. S at anything is. So if I want S at 2/3 t cubed, where I have that open parentheses, I'm just putting in the 2/3 t cubed. All right, let's just clean this up and we'll double check our point here. So that's 4 pi. If you square 2/3, you get 4/9. T to what power?
Yeah.
6.
Yeah.
Power of a power you multiply. So we have 16 pi over 9 t to the 6. This is now the surface area totally in terms of t.
It's most.
I'll go back and clean all this up in just a second. If we go back to our previous problem, we would be looking at the surface area after 1 second, which is going to be 16 pi over 9. And that would be square units because it's area. All right, let's back up and look at the answer we got. We back up. This is 4 pi. If you squared 2/3, you get 4/9, and you will get your 16 pi over 9. And they match. All right, I'm going to take it from the top because some of you are looking like you're still in a daze at what I did. Okay. All right, the problem said surface area is defined in terms of radius. Radius is defined in terms of time. If I needed the surface area in terms of time, it would just mean that, see, I've got surface area in terms of radius, that if I take what the radius is and actually plug in for R, then I will have figured out the surface area in terms of time. It's just a substitution. But we took a problem, we said, okay, well, what is the surface area after 1 second? Well, you first found the radius after 1 second, and then you put it into the formula for surface area, and you found the surface area after 1 second. Is that good? But to change it from a two-step problem to creating a function, creating a new function where surface area is in terms of time, it says I'm evaluating the surface area with respect to time where I'm using the function R evaluated at t. I put in what R was equal to, S, substituting this in for the R, there's your R right there, putting it in, cleaning it up, I now have a formula that will give me the surface area based on time that the helium or air is being pumped in versus having to first figure out the radius and then go it. All you did was put the formula for the radius in it and it took care of it. Does that make some sense? All right, let's try a couple examples that are not words. Okay, given. I think I'll just pull one right out of the book. This is page 403, and I'm just going to look at, say, problem number 12. Okay, we're going to be given that f of x is equal to 3x plus 2. And we're given that g of x is equal to 2x squared minus 1. The first part of the question uses some notation, and that is f with a little round circle and then a g and a 4. All right, this little round circle is, which looks like the word fog, but that's a little round circle. This is the notation for composition. It says the composition of f and g evaluated at 4. This says the composition of F and G evaluated at 4. That's the way you read that. And what this means is you're evaluating F at G of 4. It really means that you're going to evaluate F at G of 4. Okay? We got the words? This little round circle means composition. The composition of F and G evaluated at 4. It really means let's evaluate F at G of 4. All right, so let's just come below, and I bet you got it. All right. Remember, we always work inside parentheses first. So the first thing we need to do is go over here and figure out G of 4. G of 4 equals 2 times 4 squared minus 1, or 2 times 16 minus 1. 32 minus 1 must be 31. Okay, so we're just making that substitution. So now we have F of 31. So this says go to F and evaluate at 31. So we have F, we go to F and we have, mark that out, 3 times 31 plus 2, which is what, 93 plus 2, which is 95. Do you see how it's working with numbers?
So you just taking the answer from one function and putting it into the other one.
That's right, you're making a substitution, G of 4, substitute it into here, and then you're evaluating that function at 31. Okay? All right, that's it with numbers. Now let's evaluate it at x, which means we're creating a new function by combining these two functions. All right, so this is my own problem. F of x equals 3x plus 2, same letters. G of x is equal to 2x squared minus 1. We want to find, which means we're creating a new function, the composition of f and g at x. We're combining those two functions to come up with the composition f and g at x. All right, let's hear everybody say it. What does this say right here?
Composition of F and G at X.
Y'all are good. All right, and that really means we're going to evaluate f at g of x. Okay?
So you plug X into the...
All right, so just like you did over here, you went and found out what is g of 4. All right, so right here, what is g of x?
2x squared minus 1.
Okay, so in the place of g of x, we're going to put 2x squared minus 1. Okay, does everybody see that? And now this says evaluate f at this thing. Well, we know f evaluated at anything is 3 times the anything plus 2. So where am I putting the 2x squared minus 1? Into that little open set of parentheses, right? So we will have 3 times, and this is going to go into here, 2x squared minus 1, which is 6x squared minus 3 plus 2,
6x squared minus 1.
which is 6x squared minus 1. Okay? Now let's just do a check from the previous problem. Previous problem said evaluate f at g at 4. Well, if f at g at x, the composition of f and g at x is this thing, How do you find, if I know the composition of f and g at x is 6x squared minus 1, then the composition of f and g at 4 is just going to be 6 times 4 squared minus 1. So we got 16, oops, did I do something wrong? Oh, it is 95, I thought. Ooh, I thought the answer was something else. Okay, 16, 4 squared is 16. And 6 times 6 is 36. 96 minus 1, and we have 95, which is the same thing that we figured out on the previous page, taking it step by step, putting the number in. Okay, does everybody see that? Everybody
Where did
think
the
this?
4 come from? On the
The
bottom?
4.
Oh, you just
Oh,
checked
from the previous page.
Yeah.
I just made it up.
I didn't know what that had to do with.
Yeah, this was the answer to this question when we were finding the composition. And since that was the exact same example we just did over here using a 4, instead of going through each of those steps, once you found the composition, then you just plug and chug the
Okay,
4.
yeah, I got about that.
Okay, trying to show you a relationship there. Okay? All right, everybody good? All right, let's try another problem. I'm just going to be on page 403. Actually, I'll just let you pick one. Look at page 403, a problem between 29 and 42, your choice. Which one you want?
Let's do 38.
Which one?
I don't know, just 38 or something.
38? Okay.
That looks fun.
38. F of x is equal to x over x plus 3. Good choice of question. G of x is equal to 2 over x. Alright, the first thing you're going to do is find the composition of f and g at x. Alright, what's my next step, everybody?
Put G of X in.
Okay, f evaluated at g of x. All right, now what's going to replace this g of x that's right here?
2 over X.
2 over x. Okay. All right, now I'm going to evaluate f at 2 over x. F at anything is that anything divided by anything plus 3. Has everybody got that straight? So we have 2 over x over 2 over x plus 3. What kind of fraction do I have here? What's it called? Complex compound. All right, so let's simplify that. The numerator is already a single fraction. What do I have to do down here in the denominator?
Multiply.
Multiply the 3 by x over x so that I have a common denominator there. So I'll get 2 plus 3x divided by x. So I got the numerator to a single fraction. It already was. Now I have the denominator to a single fraction. So a fraction divided by a fraction, what do you do? Invert and multiply. Invert and multiply. And remember, when you multiply fractions, you're just multiplying numerators and denominators so that x's are common factors. They divide out. And we have 2 over 2 plus 3x. Okay? Composition of f and g at x. All right, so if you want to know the composition of f and g at 7, once you have this formula, you just go put a little 7 in for x. All right, everybody good? Okay, let's look at the composition of g and f at x. That's the part B. B, okay, let's see, f of x is x over x plus 3. G of x is 2 over x. So now we're asked to find the composition of G and F at X. How do we rewrite that?
G of F.
G evaluated at F of X. Okay, you got to be careful how you write it. It says I'm evaluating G at F of X. All right, what's my next step?
Plug in F of F.
This time we're going to plug in what F is. And F is X over X plus 3, X over X plus 3. Okay, you just follow the rules. You're working inside parentheses first. Now we're going to run over here to the G function, and where we have an X, we're going to replace that entire X with X over X plus 3. So we'll have 2 over X plus 3.
It's basically just the other way around.
Yeah, this one was F evaluated G of X. So you have to do exactly what it tells you. You got to go find G of X and then evaluate F. This one says G evaluated at F of X. So I had to go put F of X in. Then I'm going to go to my G function and substitute F into my G function. And I have 2 divided by a fraction, so you know that means invert and multiply. Hold on a second. And so we have 2 times X plus 3 over X. Okay?
What happened to the X that was underneath the 2 for the function of G of X is 2 over X?
Okay, this is G evaluated anything is 2 over the anything.
Okay, that's what you said, so that's what.
So this whole thing right here
Okay,
goes right there.
okay.
Okay? And it might be helpful to you if you do write F of anything, G of anything, and then you know you're just plugging in. That's probably a good step to put in so you don't make mistakes. Everybody good? Okay, one more of these and then we're going to jump off of this. We'll go to C part. Okay, we're still using the same numbers. F of X equals X over X plus 3. G of X is equal to 2 over X. So we were just saying F of anything is anything over anything plus 3. G of anything is 2 over anything. That may be helpful to go that direction. All right, part C says find the composition of F and F evaluated at X. Okay, you're just forming the composition. You're just creating new functions. I keep forgetting to tell you this. Look at the end. You got a whole new function when you form that composition. Over here you got another whole new function. Just like you can add functions to get new functions, subtract, multiply, divide. We're just coming up with new functions. All right, how are you going to deal with the composition of F and F evaluated at X? This is F evaluated at F of X. All right. So we have F evaluated. So you're just going to go up here and say what F of X is. And that is X over X plus 3. All right. Now how do you evaluate F at anything? You just go plug that in, right? So F evaluated anything, and our anything is at X plus 3, so we'll have, in this little first parentheses, we'll have X over X plus 3 divided by, and we got another little parenthesis, X over X plus 3 plus 3. All right? So this X over X plus 3 went inside those parentheses. Everybody see that? All right, what kind of fraction do I have here again? Complex fraction. All right, the numerator is already to a single fraction, so we're good. X over X plus 3. Okay, the denominator, we need to get it to a single fraction, so we're going to multiply it by x plus 3 over x plus 3. And that will give me x plus 3x is 4x plus 9 over x plus 3. Okay, I had two terms in the denominator, so I needed to get it to a single fraction. Two terms in the denominator, I need to get it to a single fraction. So x plus 3x is 4x, and 3 times 3 is 9. Right now I have a single fraction divided by a single fraction, so we're just going to invert and multiply. Now take it up. And when we multiply, you'll notice that x plus 3 is a common factor in the numerator and denominator. And this gives me, going up the page, sorry about that, equals x over 4x plus 9. Okay? Questions? So you just do what it says. When you're forming the composition of two functions, whatever that first one is, you're going to evaluate it at the second. Plug and chug, and life is great. All right? Okay, one little calculus concept. You're going to see some exercises. Well, let's just go to the book. Page 403. Page 403. This is actually called decomposition of functions. Let's see if your book ever calls it decomposition of functions. This is over on page 401. I don't think they call it that. I'm going to tell you, this is called decomposition of functions. Decomposition of functions. These are problems 53 through 58. What happens in calculus is you'll have to be able to break a function down into two simpler functions, f and g. And this is going to come into play when you're working with a chain rule for derivatives in calculus. All right? Now I'm going to tell you the easy way to do this, and then you never miss it. That'd be nice, won't it?
Mm-hmm. Yeah.
All right. So here's the way you do it. All right, decomposition. Basically, you're going to find two functions, find f and g, such that h of x is equal to the composition f and g at x. That's basically the way the problem works. Okay, so I'm just going to, I'll just make up an example. H of x is going to be equal to 3x minus 1 to the 1,000th power. Okay? And what I have to do is find two simpler functions that when you form their composition, you get back the original problem. All right, there's a couple ways I can talk about it, but one way I like to do is I say, okay, let f be what I call the main idea. And I'll go back and tell you what some other people call it. And I'm going to call g the details. So if you looked at h of x from a long ways off, and I tried to give you something that was a little bit shocking there, what was the main thing that hit you when I gave you that problem? That you had it raised to the 1,000th power. So if you just look at this, something is being raised to the 1,000th power. That's what I call my main idea. Some people will call that the outside function. Okay, so the big idea here is going to be f. So f of x is going to be that you're raising something to the 1,000th power. Okay, now g of x is going to be, well, what is it that you're raising to the 1,000th power? I call that the details. Other books will call that the inside function. The inside function. Okay, so what is it that you're raising to the 1,000th power? Everybody says 3x minus 1. The question was, find two functions such that when you form their composition, you're going to get back h of x. So let's just do a check. I'm going to look at f, the composition of f and g at x. F evaluated at g of x. F, g of x is 3x minus 1. What is f evaluated at 3x minus 1? 3x minus 1 to the 1,000. Okay? So when you're looking for two simpler functions, f and g, so that their composition, f at g of x is h of x, you just let f be the big idea, the type of problem that it is, and then you come back and let g be the details. All right, so let's just have a little fun. Y'all would love to have a bunch of these on the test. Let's go. We're just going to do these together. You probably got some on WebAssign, but hey, let's do it. All right, number 55. 2x plus 3 raised to the 4th. What's the big idea here? X to the 4th. So f is x to the 4th. What is g?
2x.
2x plus 3. All right, how about number 56? We have a square root of 1 minus x squared. What's the big idea here?
Square root of x.
Square root. So f of x is square root x. All right, g is the details of what you're taking the square root of. So g of x is 1 minus x squared. See how it works? I told you I could make this easy. Let's look at number 57. H of x is equal to the absolute value of 2x plus 1.
Okay.
What's the main idea here?
Absolute.
I wonder how y'all figured that one out. F of x is absolute value of x, and g of x is, what are you taking the absolute value of? And everybody says 2x plus 1. Easy, right? You can do it. Okay, I'm going to claim that you are an expert on composition of functions. You're just evaluating. The first exercise is over here. You're just doing compositions at numbers to give you some practice. We did not do domains of composition of functions, so that's left out of your assignments. And at the top of 403, you're just doing all kinds of compositions. Life is great. Okay? Play around with that. All right, let's move on into section 4.2. 4.2. And we have two topics here. Now, all of this, the reason we are doing this, if you notice the title of chapter 4 is exponential and log functions. Exponential and log functions. And this is laying the groundwork to get into the exponential and log functions. We need to understand compositions. Then we need to understand inverse functions. We need to understand these things to go from exponential to log, etc. Okay? So this sections 4.1 and 4.2 is just getting you ready for 4.3. All right, so one thing we're going to have to know is whether a function is called one-to-one. Is a function called one-to-one. Then we want to determine the inverse of a function defined by, and we'll just go by an ordered pair. Looking at a set of ordered pair, how do you find the inverse of the function? Which means we've got to know how you find the inverse anyway. What does it mean? And the third one is, given the graph of a function, can you graph its inverse? And then, number 4, we're finding the inverse of a function algebraically. Now, all functions, you cannot find its inverse algebraically. These are carefully selected problems, so don't always think that you can always find an inverse. We're having simple problems carefully selected. Okay, some people think you can always find an inverse, but you can't always find. Not express explicitly the inverse in terms of x. Okay, so I'm going to start out with what you already know, because I can look at you and tell that you already know a lot of things. All right, we're in section 4.2, and I want to just back up. What was the little line test? The line test for determining if the graph represented a function. Vertical line test. It took a lot less time for you to answer it than it did for me to write it. Vertical line test. Okay? So here's two examples. All right, here is a function, and here is another function. Okay, this is the x-axis, y. All right, so based on the vertical line test, you agree that both of these represent functions. For each x, there is only one choice for y. For each x, there's only one choice for y. Okay, now we want to go a step further and talk about what does it mean for a function to be 1, 2, 1. Anybody already know what that means? What?
It means for every y, there's only one x.
Yeah.
Okay. All right, so first of all, you got to be a function, which meant for each x there was one y. So 1 to 1, if we have a function that's 1 to 1, it already has to pass the vertical line test to be a function. So for each x there's one y. Now, to be 1 to 1, for each y, only one x. So it already has for each x only one y. Now we're going to go a step further and say for each y, only one x. All right, since you figured that out, I bet you know what little line test you can use.
The horizontal line.
Okay, now we're going to go to what is called a horizontal line test. Okay, these have already passed the vertical line test. They are functions. Now, for each y, there's only one choice for x. So basically, you're going to come through here with a little horizontal line. For each y, did it only have one intersection, meaning only one value for x. So this one is 1 to 1. 1 to 1. Now, what about this example right here? Is it 1 to 1?
Not yet.
No, this one is not 1 to 1. It does not pass the horizontal line test. Now, why is this important? Well, because we want to talk about inverse functions. So here's the rule. In order for a function to have an inverse function, have an inverse which is a function, it must be 1 to 1. Okay? All right. In order for a function to have an inverse function, that just means that maybe your function was y in terms of t. Well, maybe you want to rewrite it as t as a function of y. You want to rewrite it. In order for that to be a function, we're going to have the inverse to be a function. It's going to have to be 1 to 1. Okay, so if we come back over here, if this is our function, then to find its inverse, we're going to do a reflection across the line y equals x. And what happens when you reflect it, it just means you're interchanging x and y. So for an inverse function, so once it's 1 to 1, you interchange x and y. That means that you are interchanging domains and range, because the x value for your original function, you're going to switch them. That becomes the range of your inverse function. And the range of your original function becomes the domain of your inverse function. All right. I'm going to tell you a whole bunch of things at one time, and then we're going to come back. Let's just do an example that's going to be real easy with a set of ordered pairs so we can look at it. 1, 3, 2, 5, 7, 9. Okay, it's real easy to look at it with a set of ordered pairs. This is my function. This function is 1-to-1 because first each x value is different, and then you don't have any repeats of y values. So you have for each x a unique y, for each y a unique x. So it's 1-to-1. So the inverse function, and the notation you use for inverse is a little -1. This represents inverse. It does not mean 1/f. It's just notation. All right, so the inverse function, you're just interchanging your domains and your ranges, or your x and y's. So the inverse function would be 3-1, 5-2, and 9-7. Interchanging x's and y's. Okay? Everybody good so far? Have you heard anything you didn't already know? Anything new for anybody? Everything's new for you. All right, are you okay hanging in here? All right. So in order to find an inverse function, we're interchanging x and y's. Let's see how, given a function, we find the inverse algebraically. Again, these are selected problems. Given f of x equals 2x minus 3, find the inverse function algebraically. Okay? All right. Remember, this is the notation for inverse function. Inverse function, f with a little -1. Okay. My first question is this 1, 2, 1? This is the graph of a line, and it's always increasing. You already know what the graph of this looks like. Y-intercept is -3, slope is 2, goes like this. So it's going to be 1-to-1 because it's going to pass your horizontal line test. Anytime you have a function that is always increasing over its domain, or always decreasing, did I say increasing? One's increasing or always decreasing over its domain, it's going to be 1-to-1 because the curve, it's not going to curve back around and not pass the horizontal line test. Okay, so it's 1-to-1. All right, so basically we have y equals 2x minus 3. Now, the little cookbook for finding the inverse is to interchange x and y, solve for y, and use proper notation. All right, the reason we're interchanging x and y is because inverses are interchanging domains and ranges. So, to find the inverse, the first thing we're going to do is interchange domains and ranges. So we have x equals 2y minus 3. Okay, and now we're going to solve for y. So we have -2y equals, I'm just going to get the y over on the left, and subtract x minus 3. Y'all may have chosen to put the plus 3 over on the other side. All right, solve for y. Y is going to be -x divided by -2 minus 3 over -2, which simplifies to x over 2 plus 3/2. And we're going to use proper notation to say that this represents my inverse function. All right, let's just do a little quick check. Notice that the graph y equals 2x minus 3 has the point 0, -3 on it. Y-intercept 0, -3. So that means what point should be a solution here? if 0, negative 3 is on this curve, what point should be on the inverse? What did I interchange?
The X and Y.
I interchanged the x and y. So if 0, 3 is on this curve, what should be on this curve? Negative 3, 0. All right, let's just double check. Is y 0 when x is negative 3? Negative 3 halves plus 3 halves, 0. Okay? So any point that is on the line y equals 2x minus 3, if I interchange the x and y, it's got to be a point on the inverse function. All right, so let's just back up and sort of summarize, and then we'll stop here. We have a little bit more to do there. Okay, if we have a function that's 1-to-1, okay, it's already passed the vertical line test to be a function, correct? 1-to-1 means go back and check out the horizontal line. So a function, for each x, there's only one y. For each y, there's only one x. Okay? So therefore, you can have an inverse, which is a function. Inverse means interchange x and y, or interchanging domains and ranges. All right? So to solve algebraically for an inverse, the first thing you're doing is interchanging your domain and range. That's why you interchange x and y. You interchange domains and ranges. If you solve for y, you now have your inverse function. You can always easily check that you haven't made a mistake by getting a point on the original function, interchanging the point, the x and y coordinate, and it should match up right here. Okay? All right, be sure you read your textbook. There's a lot of valuable information there, and we're going to pick up with 4.2 tomorrow, cover 4.3, and that will be where test 3 ends. Make it a great day, everybody.